We were discussing the Faber-Jackson relation, which is that the luminosity, well, it's analogous to the Tully-Fisher relation, which is that the luminosity is proportional to the maximum velocity to the power 4. And in this case, its luminosity is proportional to the velocity of dispersion to the power 4. And you can write it like that, which we discussed. And then, as I said, you can use this, you can measure the velocity of dispersion fairly easily. And so that means you know the total luminosity and you know the apparent luminosity, so you can hence get the distance.
Yeah.
Yes?
How do you measure the velocity of dispersion?
By measuring the systemic velocity and the velocities compared to the systemic.
Is it just that? Okay.
Yeah. The velocity of dispersion is just it's the square of the average velocities. Right? It's the average of the square of the velocities. Sigma squared is the average of all the v squareds.
Yeah.
Okay. Right. So the Faber-Jackson relation is a consequence of the virial theorem. And as I said, there's a derivation of that on Moodle, but you've probably seen it before. And for n stars of mass mi, the kinetic energy is just a half mi vi squared. And I think I went through this. The total mass is n times n, so the total kinetic energy is, taking this 2 over here, 2t will be m, the sum from I equals 1 to n of m times vi squared. If we assume a total radius r, then for a constant density sphere, the gravitational potential is 3/5 gm squared over r. That m is the total m. So if 2t is equal to the magnitude of omega, here's 2t, that means the sum of m times vi squared is the magnitude of omega, forget the minus, so it's 3/5 gm squared over r. And we usually measure the radial velocity from the Doppler shift, and by Pythagoras, the actual velocity will be the radial velocity, v squared, will be vr squared plus the theta component squared plus the phi component squared, okay? If we assume that the velocities are isotropic so that we've got just as much chance to be oriented in one direction as the other, then these on average will be the same. And so that v squared will just be the sum of those, and each one of them is the same. So it'll be 3 times whichever one we can measure, which is the radial one, will be sigma squared. Okay? So that's how we do it. We measure the radial velocities, multiply it by 3 after subtracting the systemic velocity, and that's 3 times sigma squared. Okay, so now going back to this, I've got 1 on n times the sum of the vi squared, because that was an mi vi squared. Oh no, sorry. The average v squared is 1 on n times the sum of the v squareds, and that's just 3 sigma squared. So now I go back to the equations. M times the sum of the vi squareds, which is just 3 sigma squared times n, is 3/5 gm squared. So that becomes m times 3n sigma squared is 3/5 gm squared over r. Getting rid of the m on either side, because m times n is capital M. And so then I get an expression for sigma. Sigma squared is 1/5 gm on r. Now we can measure sigma, and we can sort of measure r off the sky, so that tells us m. So the idea is to take that equation, evaluate it at RE, the effective half-light radius. So sigma E is 1/5 gm on RE, and everything there is known and measurable, and that defines the virial mass. So the virial mass is 5 sigma E squared RE over G. Okay?
And what is the virial mass?
It is the mass that it would have if it was in virial equilibrium, if 2t was equal to omega. Just gone back further than I...
Can't any mass end up in equilibrium though?
Sorry?
Can't any mass end up in equilibrium though, given enough time?
Depending on the velocity dispersion, it will alter its velocity dispersion.
Yeah.
So for the velocity dispersion that we measure, that would tell us what the virial mass would be if what we're seeing is virialized.
Yeah. So it's a bit backward because usually it works.
Well, you can't, I mean, they may not be virialized anyway, so that's an assumption.
Yeah. But it's not, the mass doesn't change to make it virialized, the velocity does.
That's right, yeah. Yep. And so we're measuring the velocity and then saying, well, if it's virialized, then the mass must be blah. Okay. So these dwarf galaxies have sigma squared proportional to the virial mass, and for disks, am I hitting the wrong button? Nothing happened. For disks, we had the velocity squared was proportional to the total mass. Remember, for disks, we derived the Tully-Fisher relation. Now we're doing the Faber-Jackson relation. We're going to make the same assumptions. For disks, we then assumed that we had a constant mass-to-light ratio and a constant peak surface brightness. And then we got the Tully-Fisher relation, which was L was proportional to V max to the power 4. So we're now going to make the same assumptions here. Constant mass to light and constant peak surface brightness. And then we'll derive the Faber-Jackson relation, L proportional to sigma to the 4th, where this is the central value. Okay, so we start with sigma at the effective radius, the half-light radius, is 1/5 g m virial on Re. We know that the luminosity is, remember, if you integrate from over the entire disk, then you get something in terms of the values at the half-light, which is what we can measure. So that means that Re squared is proportional to L over IE, and sigma e to the 4th then will be m squared over Re squared. The Re squared I put an L over IE, so it's m squared on L times IE. So if I multiply by an L and divide by L, that's m squared on L squared times LIE. M squared on L squared is just the mass to light ratio squared, and we've assumed that the mass to light ratio is constant, so that says that sigma to the 4th is proportional to L times IE, and if we assume that the surface brightnesses are all similar, then sigma to the 4th is proportional to L, and that's exactly the Faber-Jackson relation. Okay, so it's in direct analogy with the Tully-Fisher law, and so they're both the same physics involved. So this is part 2 of the elliptical galaxy stuff. These galaxies are too far away to observe individual stars, and so the poor people working in this field are used to use integrated spectra to try and work out what's going on, which is a real problem. So here's your typical kinematics for an elliptical galaxy. This is a radial velocity measured across the face, and so you can see there's clearly some rotation in here. And this is the velocity dispersion, and it's certainly it's higher in the centre. In fact, this is a delta V of about 80 kilometres per second, and this is in the way you would expect for rotation. It's blue shifted on one side, red shifted on the other, so that means you've got a rotation there with a total change in velocity of about 80 kilometres per second. This is the velocity dispersion about the mean, and it's about 300 kilometres per second. So that tells you that the random motions about the mean are a lot more than the rotational component. Okay? So that means that the rotation is not important for, not nearly as important as the random motions in this galaxy.
Sorry, if the velocity dispersion is so great, how the... Oh, I suppose it's relative...
It's a dispersion relative to the central, relative to the local velocity, yes.
Yeah, but I was just talking about the like error bars. I suppose it becomes they're relative to like physics.
I believe so. Yes. Yep. Oh yeah. Well, this is really exciting stuff. I'll try to not communicate that I don't find it very exciting. John Cormandy, I think he was at University of Toronto when I was there, found that in general the effective radius was related to the surface brightness in this way, proportional I to the power minus 0.83. And the Faber-Jackson relation, we just saw that's L's proportional to sigma e to the 4th. And but there was more scatter than comes from observational errors. So the point was, is there some way these can be combined? Is there another function going on here that we haven't recognised? And these characters discovered that these are different projections of what's called the fundamental plane. And they showed that Re is proportional to sigma to the 1.24 times I to the minus 0.82. That is the relation. It actually relates all three things together, and then we have projections of one onto the other, but there's a lot of scatter because of the third variable that's not being used. And that's called the fundamental plane. It's used to estimate distances. Again, you measure sigma from Doppler, motion, and IE from surface brightnesses, and hence you can calculate RE in kiloparsecs and measure RE in seconds, and so that gives you the distance. And this is an example showing you what that fundamental plane looks like in 3D, where you have your 3 different dimensions. And if you look at a projection in 1D, you can see that in any two dimensions, you can see that relation, but it's actually much tighter in 3D. Okay, that's just so you recognise the word fundamental plane if you come across it. Now, if you assume that the observed ellipticity is due to rotation, and there's an isotropic velocity dispersion, then one can show, I'm not going to do that, that the rotational velocity over the dispersion is related to the eccentricity of the velocity field, of the stellar distribution. It's a square root of epsilon on 1 minus epsilon. So we then define V over sigma of the star to be V rot over sigma observed over the isotropic value. And we arbitrarily say a galaxy is rotationally supported if the actual value is greater than 0.7 of the isotropic value, okay? So remember, the isotropic value will give you that value of sigma. So if the observed value is greater than 0.7 of the isotropic, we say, okay, it's essentially the isotropic value, and that's where the eccentricity is coming from. The bright giants have V over sigma star around 0.4. The brightest galaxies get up to 0.9. So some of the ellipticals are rotationally supported and some aren't. That's the take-home point. That was how we get there. I don't expect you to go through that. Now this is a variation. This is shows you the variation of A4. Remember, A4 was the variation, the fourth order, fourfold symmetry variation from the best fit ellipse to an elliptical shape, and compared to V over sigma, which tells you the rotation. If A4 is less than 0, then we have boxy isophotes. So here's the line A4 equals 0. This is A4 down the bottom, or 100 times A4 over A. So this is A4 on the bottom. So now I'm going to have a look at the variation of A4 and V over sigma. So here's V over sigma here. You'll notice all those with A4 less than 0 have got low values of V over sigma. Okay, that means that there's very little rotation and they must be supported by the random velocities. Now if we have a look down here, this is the mass to light ratio, m over L, and again all those with A4 less than 0 have got a bigger spread of mass to light ratio than these ones. Okay, so and a higher mass to light ratio in average. Over here, this is the radio luminosity, and this is the luminosity in the radio. And so again, those with A4 less than 0 have got the largest radio output compared to those that have A4 greater than 0. So they're radio loud objects, and I'm not going to discuss this one. So now if we have a look at all those with A4 greater than 0, these are disky objects. Then here's the A4 equals 0 line again. And so up here, these have got a much higher V over sigma. It's around 1, so that means that there's more rotation. They're essentially rotationally supported. If we move down here, the mass to light ratio in this case is lower than average. And again, the radio luminosity is lower on average. So they're radio quiet. So there are clear correlations that theorists then have to explain. And we're not going to go into that, but the idea is to make you aware of these different phenomenological descriptions. I would find this way too dissatisfying. Dissatisfying. I use the word dissatisfaction. It's in that TV show. Unsatisfying. So, do ellipticals have dark matter halos like spirals do? Near the centre, we think the mass to light ratio is around 3 to 5, and in the outer regions, it's about 20. So that means that there must be dark matter in the outer parts. And you can look at the motion of globular clusters, and again, we get mass to light ratios around 50. So that means that the elliptical galaxies do indeed have dark matter halos. You can't explain their dynamics without it. And we believe that there are supermassive black holes in the centre of many of these galaxies. In the Milky Way, we have a small supermassive black hole, which might just make it a massive black hole, you would think. But a massive black hole would refer to a stellar mass black hole. So anything that's more than stellar masses is called supermassive. So hence you can have very small supermassive ones. And this affects the velocities of stars in the thing, and I showed you this before. This is the orbit of star S2 around the supermassive black hole. And I think it then zooms in on it, doesn't it? From memory? Yeah. So it's pretty impressive. I mean, they're actual orbits. They're not simulations. That's actually observed, or actual observed orbits made by ESO. And you'll notice the speed increased dramatically near the perihelion here. Very impressive. Okay, so supermassive black holes in galaxies. If we look close enough to the centre, you should see the effect of the black hole on the velocity dispersion. And if you get close enough, then the velocity will exceed the overall dispersion, whatever it is. If you get really close, then the acceleration caused by that should exceed the velocity dispersion. And so you can then work out if v squared must go like gm black hole on r, has to be greater than c squared. You can work out what the radius must be for this, how close you have to get in to observe this, depending on the mass of the black hole, of course, and sigma. And so that's that expression, and this is the empirical relation between sigma and the mass of the black hole. And this is an example showing you that relation and all the different black hole masses as a function of the velocity dispersion. So that's where this formula comes from. And we'll come back to that when we discuss active galaxies in lecture 30-something. Now, observations show clear evidence for the mergers of galaxies. These are some pictures, and there's some coming up soon. There's some really good pictures coming up. I think, is that called, here I'm trying to remember the name. I was going to say, I think it's called the mice. It's called the mice. This is the same thing in radio images from neutral hydrogen. And this is an n-body simulation. And you can see it fits remarkably well. I did some stuff like this where we were looking at collisions between interstellar clouds to try and get stars to form. And so you take a couple of clouds and you make them spheres because you don't know what else to start with. And of course, you look out in the galaxy and there are spheres of gas everywhere. So anyway, you throw them together, and we then calculated the CO emission along different lines of sight, and then we would rotate the thing by some random amount in some random direction. Then we measured the CO absorption again, and then we would plot up contours of what the CO looked like. And then we looked at weird CO contours in the galaxy, and we found a number of things that looked like they could be a collision viewed from some weird angle. I think that's one of the nicest papers I've ever done. No one ever cites it. You can only do so much, So here's a numerical simulation. This is the mice, and this, I'm going to have to do this, but I think this is a movie that simulates the mice. It's a little bit blurry, isn't it? Well, it could just be my eyes. So it doesn't do a bad job of looking like the mice galaxies, does it? Well, I mean, it's evolving, so you have to stop it at the appropriate time. So you must just about have a code that can do this. You went to n bodies today, is that right? N objects.
I mean,
Sorry?
generalized, but yeah, we only actually.
We only use 2 bodies.
You only use 2?
Yeah.
Okay.
But it can do as many as the computer can.
Yeah, yeah, that's good.
Yeah.
I think next week the lab's set aside for you to work on the assignment, and the following week you actually make a couple of galaxies. You sort of take a point, I think there's a point mass in the centre, and then you put 100 particles around it, and then you do the same thing somewhere else on a different angle and just let them fall together. It's good. Okay, so let's have a look at the energetics of some collisions. Oh, I better turn this back on. So suppose we have 2 galaxies that are initially virialized so that 2t plus omega equals 0. And the subscript I just means initial, and both galaxies are the same. So omega, the initial gravitational energy, is minus 2 times the kinetic. And the total energy is just the kinetic plus the potential. And so if omega is minus 2t, then that's t minus 2t, or EI equals minus TI, or minus omega I on 2. Now obviously the total energy is negative because it's bound. Okay? So it's virialized, the energy is equal to minus the kinetic. Now when these 2 galaxies collide, the kinetic energy will increase. They'll be accelerated towards each other by gravity. So the final energy will be the initial energy plus whatever the kinetic energy was. So the delta T will go up by this. And after the collision, if it's again virialized, the final energy will be minus the total energy will be minus the final energy, which is minus EI plus delta T, which will be TI minus delta T. So that means that the kinetic energy is actually decreased by the collision. So the internal kinetic energy is decreased by the collision. That's right. So how do the galaxies remove that energy? By gaining potential energy. So what they'll do is they tend to increase in radius and puff up. And you saw that in the previous thing, right? In the previous movie. There's stars being thrown out and expanding as a way of conserving the energy. They could also eject matter through streams of gas and dust, as well as the whole galaxy puffing up, and both processes do occur. Now you can classify your collisions. I don't find this the most satisfying stuff, but nevertheless, there are minor mergers and major mergers, and there are wet ones and dry ones, and you'll never guess there are damp ones. A minor merger is where one galaxy is much, much larger than the other. Okay, so it's just a minor perturbation to the big galaxy. A major merger is where they're roughly equal masses, so it's a big effect on both galaxies. And this causes this burst of this gravitational perturbation can cause dramatic burst of star formation in these galaxies, and also active galactic nuclei and quasars, and can produce an elliptical galaxy. So minor merger is where you're just adding a small thing into a big one. A major merger is where they're both the same size, roughly. A wet merger is between gas-rich galaxies. They're wet in the sense that they're able to make lots of stars. A dry one is where there isn't very much gas to make stars, and a damp one is something in between. And then there are mixed ones where one has gas and one's without. And it's not very satisfying. And then if you collide galaxies head-on, you can make these these ring galaxies, where you have an elliptical galaxy in the middle and a ring of stars around the outside, which looks very much like a spiral arm, but it's in the form of a ring. That's not a simulation, that's an actual photo.
What do you mean by head-on? Like the spiral just falls directly onto the elliptical? And it
I think that's what it is. That's a good point. I don't remember.
You get a body, you get like a flat disc, and you get a body basically passing through it, like that.
So it's just a zero impact parameter. So it's head-on in the sense that there's zero impact parameter, but they don't have to be like this. It just it could be going like that.
Yeah, I guess,
Yeah.
Yeah, and then basically as it passes through, it just strips everything out.
I'm not sure whether I've got a So that... Sorry, I missed that. What was that?
It's like a Beyblade.
A what?
Never mind.
It's a toy you spin.
Oh, a spinning toy. All right. Sigh. And this is so this is viewed head on, but if you look at it sideways, it looks like that. So the other one was viewed down this way. Okay. And this is believed to be the same thing, but just viewed from a different angle. Sorry?
How? How would we get those two pictures?
Oh no, they're two different examples.
Oh.
But it's thought that no, it's a good point. We sent a spacecraft out 50 megaparsecs and waited for the image to come back. No, it's two different examples, but believed to be of the same thing. And this is looks to be a normal elliptical surrounded by a ring of dust and gas, as you can see in these maps. And this is how you can make this. I couldn't get a movie for this. This is a bunch of stills showing this. I'm not sure what the blue galaxy is. This is clearly meant to be a spiral. And the blue, I'm guessing the blue is just an elliptical galaxy. It's a spiral that gets torn apart into the rings. Material believed to have been stripped from the galaxies during the pass-by or merger. Yeah. Yep. And starburst galaxies, Richard Larson. Richard Larson is a Canadian, used to work in star formation, so that's how I know him. And Beatrice Tinsley found that the interacting galaxies on average were bluer than isolated galaxies of the same type. And I was about to say what makes them blue, but the very next line is a giveaway. The blueness is massive stars, so that would probably mean recent star formation. So they claim that there was some interaction. The interaction here had produced a burst of star formation, and sometimes we call these starburst galaxies. And most star formation is confined to the inner kiloparsec of the core, where the density is the highest, and we can get, these are pretty impressive star formation rates, 10 to 300 solar masses per year. The bursts may only last for 10 to the 7 years, but the phenomenon itself lasts for 10 to the 8 or 10 to the 9. So each burst goes until you use up most of the gas in that gas cloud, and then there's another one from the perturbations and the collisions that continue. This is the antennae galaxies, and there's a simulation here. You're probably going to laugh at this too, because you're hard people to please. This attempts to make these. There you go, it's not too bad. Of course, you have a lot of parameters to play with.
There's a supernova in the other image.
With this, or that, and they could be foreground stars as well. Or supernovae. Probably a foreground star. So that does look pretty much like that sort of thing. Now we're just zooming in on the centre of it. Finished? Seems to be finished. Okay, so CD galaxies, and as I said, I don't remember where the name came from, but I didn't find it. Sorry? That's a good way to think of it, but I'm sure it wasn't that, because that would have made sense. Really?
Yeah.
No, that's going to be a what they call a back formation, surely. Because I thought I read somewhere that it was a variation on a C-type or a D-type of galaxy. Maybe I'm completely wrong. It wouldn't be the first time. No, it would. I've been partially wrong a few times, but never completely wrong. So no, these are the most massive, and they're never found alone. They're only ever found in the centre of galaxy clusters, and that's a substantial hint to their evolution or their origin. And more than half of them are observed to have multiple nuclei in the centre. So it's quite likely that they all do, and we just haven't been able to observe them because of projection effects. And they have typical orbital speeds of stars in these things of 300 kilometres per second, but the nuclei are moving at around 1,000 kilometres per second. And so this indicates that this thing has formed from a merger and puffing up of the galaxy, which will cause the stars to slow down. So some galaxies have come together, at least two, have come together and they've merged. The puffing up that's necessary because of the kinetic energy, the acceleration, causes the stars to move out, and then the outer ones are moving slower, but you've still got these cores of the original galaxies going around each other inside at high speed. Okay, so the origin of the CD galaxies is thought to be mergers. More than two galaxies, no doubt, but at least two. But often
Speeds, dispersion or rotation or velocities?
they'll be dispersional velocities. They'll be random velocities, I should think. Yep. More than half of the known elliptical galaxies show faint shells. And here's some pictures. Note the faint shells. And this one's really quite impressive. And these are again thought to be due to nearly head-on collisions between galaxies. I don't know whether that's a movie or not. Let me just see if I can get any sense out of it. It is. Doesn't seem to be. Oh yeah, it is just slow. So you can see shells of star density here, right? Quite well-defined limits when stuff gets ripped apart, which would appear as a brightness, a shell in brightness. But they're actually just limits to the orbits of the stars. Carlos Frank. Right, that looks like the end of that one. Okay, so let's have a look at some of these interacting galaxies. Hello, thank you. Having a very serious experience. The box is happily recording, it's just the it's reality that's at fault. Not for the first time, in my experience. Okay, so if you can just sort of black out when that's black, and you'll find everything's fine. This is pretty damn annoying, so maybe we'll stop here, eh? And we'll ask IT to come and have a look at that. There's no lecture tomorrow, is there? No. So there's a very small chance they'll actually fix it before next week.
Does that mean you're just going to go past the next class?
No, I don't think so, because I think we're doing okay. We've got six lectures left or something. Well, we're 2 lectures ahead plus I'm 1 lecture behind, because I can't count.
We're still 1 lecture ahead.
So we're still a lecture ahead. So I think we're doing okay.
Hang on, we've got okay, spiders now.
It is indeed pretty annoying, I agree. Well, you just have to stand there. Okay. Okay, we've... I moved. You sure it wasn't just the fact that I spoke? Okay, so isolated versus interacting galaxies. The definition here, I find this whole field just a tad non-quantitative and a little annoying, you know. It's isolated if it's not affected by another galaxy in the last few billion years, and it's interacting if it is. Well, yeah. Well, what is interesting, I guess, is that most galaxies are not isolated. So M31 or Andromeda is seemingly isolated, but we know that that is actually going to collide with us in about 4.5 billion years. And the Sunflower Galaxy seems to be isolated, but there's a recent burst of star formation, so maybe something perturbed that. So if you want to have a look at the interactions between galaxies, we need to remember what they're composed of. Stars, here's some stars for you. Gas, here's some gas, and this is dark matter. Is there any end to my wit? You don't need to answer that. You could say, is there any start to it? Yeah, someone did, right? Okay, so how are these things going to interact? Stars only interact through gravity. It's not quite got the size right, but at least it's stopped flickering, and on cue it flickers. So we know direct collisions are negligible between stars. So the galaxies are not gases, right? In a gas, the whole idea, the pressure of a gas is caused by frequent interactions between the particles. Galaxies aren't like that. They're collisionless. The stars are so far apart that they don't affect each other, and except through gravity. So the only effect here is from the gravity of the stars. Collisions between the stars are exceptionally rare. Gas, thank you. Gas interacts through gravity and also through shocks and dissipation. So if you throw two streams of gas together, or a liquid like that, when it hits in the middle, they don't pass through each other. Two streams of stars would pass through each other. And then they'd be pulled back because of their gravity. Gas will shock, will at least be compressed, and dissipate energy through heat. Okay, and a liquid is just a gas, which is why hydrodynamics is not really hydrodynamics; it's really fluid dynamics, because hydro means what? Right. So you'll see people will all the time refer to hydrodynamics when they really mean fluid dynamics, because they're doing gas dynamics and not water. Water is not compressible; tiny little bit of compressible. You can push on water, and you can't change its density by a factor of 2 very easily. And then there's dark matter, which only interacts through gravity. Okay, so these three things behave differently. So billiard balls with no gravity would just go straight past each other like that. Point masses with gravity, they then pull each other towards each other, and they will end up on elliptical orbits. If they are extended masses, not point masses, but extended masses, then you can get interactions between the spin of the thing and the orbital energy. You can get transfer between one and the other, and then you can start to dissipate the energy in the star. Hello? In the ball of gas, because it's no longer a point particle, right? It can now dissipate energy within it. And in that case, this is a real calculation, these things change their energy, their behaviour completely, and end up merging here. Okay, so dissipating energy makes a big difference. One of my physics lecturers, when I was a student 100 years ago, Harry Perlman, you'll remember Harry. I may have told you this. I think this is one of the great lines of physics. And again, I'm a bit mental. He was talking about point masses. Some student put his hand up and said, "What's a point mass?" And Harry gave the perfect theoretical physicist explanation. He said it is a particle with no internal structure, which is, as Douglas Adams would say, true but unhelpful. I mean, if it has no internal structure, it is a point particle. But anyway, this kid didn't understand. And he said, "You mean it's hollow?" And Harry gave the perfect answer. He said, "No, it's too small to be hollow." I love that. That's a theoretical physicist answer. It's too small to be hollow. Now that seems to be the same thing. Okay. Galaxy collisions, calculations versus reality. Is this the movie? This is a good movie. This is worth seeing. One of the few. There's no movie there anyway. Maybe there's a movie here. Yeah, okay. This is a simulation. And there's reality. So what this movie will try and tell you is that there's been a number of things that are observed are consistent with this calculation just seen at different epochs. One's a little bit of a stretch, but not too bad. Here's your mice. Is it, or is it the antenna? I can't remember.
Was it the previous one?
Maybe. I can't remember. Not so sure. But now that we can do pretty realistic, or what we think are pretty realistic calculations like this, then we can actually start to understand some of the things that we see. Now this is a calculation showing the collision of Andromeda and the Milky Way. I think there are some numerical problems with this, because there's way too many stars being thrown out at high speed. What could cause a star, in a calculation, what could cause a couple of particles to be thrown out at high speed? It's your gravitational potential, and what's called hard binaries. If these two particles get too close together, then because you're not taking a time step small enough to resolve their orbit around there, then you take a time step and there's a huge force and they get thrown a long way out. It's a problem that used to happen regularly in the early days of in-body simulations. And although, you know, it's not, we've got various ways of counteracting it, I think it happens too often here. Thank you. I think this is the one. Oh, this one's got fancy music too. Sorry, annoying. Ooh, why did it do that? Should I turn the music off? No. Oh, okay. Some of that must be real, the puffing up. It's definitely the projector, right? Because you can see it's trying to select its input up there. It seems to lose it every now and then. Okay, I'll give up. I'll play this one again on Tuesday.